Hello everyone, I am Haoyun and thank you for coming. Today I am going to talk about uncertainty quantification for Hawks networks. This is a joint work with Liyan, Alex Cuozzo, Simon Mack, and Yao Xie. We are from Georgia Tech and Duke. Nowadays we have many networks, for example, social networks and neural networks. And on these networks, we observe a series of events happening on these nodes, and we would like to make inference on the influence between the nodes based on these event data. For example, in the social network, the event can be some user posting a tweet about a certain topic. And if user A have an influence on user B, it is likely that after user A posts a tweet, user B would post a tweet on the same topic after a few hours. In the neural network, the events can be the spike train on each neuron, and after an excitatory neuron spikes, it is likely that the connecting neuron would also spike after that. So this is the kind of influence we would like to discover. We can model this using a point process. A point process consists of a series of events happening at T1, T2, and so on. The intensity function of this point process can be defined as lambda t. It is the probability that an event happens during an infinitesimal period of time. And we can define the counting measure on this point process as the number of events happened during time 0 and time t. We define the integral of a function f with respect to the counting measure as the sum of f where event happens. And more specifically, we would like to model this as a Hawks process. A Hawks process is one of the point processes where the event would have a positive influence on the future. So the formalization is like this. The influence of the point process is the sum of the base intensity and the sum of the influence of past events. Here, phi is the kernel function. It describes how an event will influence the future, and this alpha is the self-influence factor. It describes how much an event will influence the future. And in this simple illustration, we show the intensity of a Hawks process over time. We can see that whenever an event happens, there is a surge in the intensity. And that's how we say the events have a positive influence over the future. We can also expand this Hawks process to a network setting. So here, instead of the event times, we have the event times with its location, UK, and UK is one of the D nodes. Each node has its base intensity mu I, and each pair of nodes has the influence factor alpha ij, which is larger than 0, and the kernel function phi ij. Here, this alpha ij is not necessarily equal to alpha ji. This means that the influence between the nodes is asymmetric. And the intensity of node I is the sum of the base intensity and the influence of past events. Here in this illustration, each row represents the events of one node, and we can see that the events on the node can trigger both the events in itself and in other nodes. And this is how the Hawks network works. So now, given the base intensities and the kernel functions and the event data, we would like to make inference on the influence factors alpha ij. And most importantly, we would like to see whether this alpha ij is 0 or not, because if alpha ij is not 0, we will say that node j has an influence on node I. And we can formulate this as a hypothesis testing problem by setting the null hypothesis to be alpha ij equals to 0 and the alternative hypothesis to be alpha ij larger than 0. First, we begin with the maximum likelihood estimate of alpha. It is a good estimator because the optimization problem is convex, and so we can use convex optimization to find the MLE, and also the log likelihood function is decoupled for each node I. To be specific, we can see that the log likelihood function can be written as the sum of the terms, and each is only relevant with this alpha I, and the alpha I is the influence of all the nodes to node I. So this way we can separately estimate each of the alpha I and do the uncertain quantification on the alpha I's. So, and next we would focus on estimating and providing the confidence set of only one alpha I. In 1996, Ross-Wang also states that the MOE of this Hawkes process is consistent and asymptotically normal as t goes to infinity, so MOE is a good estimator. Here, the capital I is the phasor information. Now with the asymptotic normality, the classic CI just use this property. So the vector alpha I is asymptotically normal, and if we look at each entry, the alpha ij's are also asymptotically normal. Here, the sigma ij is the corresponding entry in the inverse of the phasor information. And the asymptotic confidence interval would just be the MLE plus or minus this term, where the d value is the corresponding quantile of a standard normal distribution, and this sigma hat is estimated from the data. The problem with this asymptotic confidence interval is that there is no guarantee when t is small. And the reason is as follows. First, we define SIT as the score function up to time t. The score function is the derivative of the log likelihood function. And here in this plot, we show the variance of the increment in the score function over time. And here, the phasor information is the average variance of the increment of the score function. It is plotted in this yellow line. We can see that the variance of this variance is really large. And if t is not large enough, and we use this observed variance as the phasor information, it can be far from the truth. And this will result in a confidence interval that is either too large or too small. So here we come up with a confidence set with theoretical guarantee. It is based on martingale inequality of the score function, and we jointly perform uncertain quantification on this vector alpha I. And after we getting the confidence set for this vector alpha I, we can project it onto each entry to get a confidence interval on each alpha ij. Then during this process, we decide on the parameters adaptively, and also we can use first order Taylor expansion to get a nice form of the confidence set as well as simplify the computation. The difficulty of having a having a concentration inequality on the score function is that, as we've shown before, the variance of the increment in the score function can vary over time, and actually it cannot be bounded from above. So we cannot use a traditional martingale inequality to do this. Now what we do is use the intrinsic variance. This is introduced in Howard's paper. It used the variance we observed to decide on the size of the confidence interval. So if the observed variance is really large, we would have a large confidence interval. Here is our mean theorem. It states that for a vector z that is adapted to the same filtration with the Hawkes process, the score function projected onto this vector z cannot be too large. Here, this term vi is the so-called intrinsic variance. You can see that it is the integral of the log moment generating function of the increment of the score function over time. And this vi is designed to be of the same magnitude of log 1 over epsilon, so that we have a reasonable bound on this score function. The next thing to do is decide on the choice of z. Here we choose 2 times the different values of z, and each corresponds to the upper or lower bound of the alpha ij. And they look like this term below. Here we don't know the true Fisher information, so we use the empirical Fisher information instead. And note that to estimate z at time t, we only use data up to time t to estimate this empirical Fisher information and to estimate this z value. Now with this choice of the vector and the concentration inequality, we can define 2D functions called g on the parameter alpha I, and this form is exactly the same as in the concentration inequality. So we arrive at the confidence set of alpha I. The set is consists of the alpha I such that all of these g functions is not too large. And this is a confidence set with theoretical guarantee. After getting this confidence set, we can project this confidence set onto each entry and we'll get the confidence interval for each entry. Now the problem with this method is that to solve the confidence interval for each alpha ij, we need to numerically invert the g functions, and this can be time consuming. So we come up with a first order approximation of this gk. And our final algorithm is like this. So for the input, we have the confidence interval minus epsilon, we have the event data, and we have a reasonable estimator of the Fisher information. First, we compute the MLE. Then with the MLE, we compute the g function at the MLE as well as the first order derivative of the g functions at the MLE. Then we approximate the g function using first order Taylor expansion rooted at this MLE, and our outputted confidence set is the set of alpha such that the approximated g function, all of the approximated g functions is not too large. This way, actually we get a nice polyhedron as the confidence set, and the number of constraint is 2 times d. So with this polyhedron, we can solve for the confidence interval for each alpha ij by linear programming. So here is a simple example of how our confidence set looks like. We use a toy model with only 2 nodes, and here the green diamond and the green ellipsoid is the MLE and the empirical Fisher information. Based on that, we have the asymptotic confidence interval in the red shaded box. We can see that it does not contain the true parameter. And these 4 blue lines are the solution to the function g alpha I equals to log 2d over epsilon. And the area cornered by these 4 blue lines is our confidence set. The blue shaded area is our polyhedral approximation of this confidence set. And we can see that it contains this true parameter. And we can also see that this area resembles a box because that's how we design the z vectors. We design the z vectors so that the edges of this polyhedron should be parallel to the axis. Now we come to our real-life application of this algorithm. We use a neural network of size 32, and the data is generated by this neuron simulator. As I understand it, this data, the neuron estimator generates data based on the electrical and chemical nature of this neuron activities, and by solving a very complex differential equation. So here, the data is not generated using a Hawkes process, but since there are environmental noise, we can think of it as a random point process. And this is our result on this model. So the first figure shows the true parameter of this network, and the second one shows the estimated alpha ij's of this network. You can see that this is very dense, and that's why we would like to do hypothesis testing on whether the alpha ij's are larger than 0 to get a reasonably sparse network. In this case, the asymptotic confidence interval is too wide and it covers everything. Our proposed method have a reasonable coverage rate at 96%, while it's designed to cover 95% of all the edges. And in figure 3, it shows all the edges that is not covered by our proposed method. And interestingly, all these edges are supposed to be non-existent, while our confidence interval shows that it should exist, meaning that the confidence interval does not contain 0. And in the fourth figure, we have the difference between the widths of the two confidence intervals. And we can see that the asymptotic confidence interval is generally wider than our proposed method. And thanks for coming to listen to my talk, and I will see you at the question sessions. Thank you.